We've seen this equation before. It's how you calculate gravitational field strength G at some distance r from a mass m. But let's see it in action. Here's the Earth. I'm going to pick a point right here, about 9 million meters from the center of the Earth. So we use the equation to find the gravitational field strength here. In other words, how strong is Earth's gravitational field at this point? So here's the equation. First, we need the value of g, the universal constant, so we look it up in our data booklet. Then we need the value of m, the mass of the Earth. A simple Google search, mass of Earth, shows us the value that we need. Let's plug that value in here. And lastly, right here, we need the value of r. You might think that r is the radius of the Earth, but actually r stands for the distance from the point where you're measuring the field strength to the center of the mass. So it's this distance. And we chose a point randomly that was 9 million meters away. When you do this calculation, what do you get? 4.92 newtons per meter. But wait, what if we chose a point that was right here on the surface of the Earth, and we calculated the value of g right there? After all, don't we know what g equals at the surface of the Earth? Isn't it 9.81? Let's see if this equation has anything to do with that same g. Okay, so once again, we have to plug in first the universal gravitational constant. Then we plug in the mass of the Earth, which is the same as above. And what's the value of r that we need to plug in? Well, remember, r is the distance from the point you're considering to the center of the mass. So in this case, r is actually the radius of the Earth because we're considering a point at the surface of the planet. To find the Earth's radius, let's go to Google. A simple Google search shows that the radius of the Earth is 6.371 million meters. Let's use that value. So I plug in the value here, 6.371 million, or 6371 in 3 zeros. This next part is a little shocking, so I want to show you on my calculator that there's no funny business. I type 6.67 second EE to the negative 11 times 5.972 second EE to the 24 divided by, 6371000 squared. And look at what I get, 9.81. So in fact, right here at the surface of the Earth, the value of g is 9.81 newtons per meter. And as you go farther away from the Earth, the value of g decreases. That might sound kind of fishy to you. The value of g decreases the farther away we go from Earth? Well, here's the Earth, and here's a person, and maybe they're holding a ball, and they could possibly launch the ball. But maybe there's a bird nearby, even higher up. So the value of g is smaller for the bird because it's higher, and the value of g is bigger for the person because they're closer to the Earth? Well, not exactly. Here's the equation again. We plug in the value of the universal gravitational constant. Right here we put the mass of the Earth, and here we put the radius of the Earth. All of these objects have the same value of g. And the reason is because if you add 2 meters for your height, or if you add 5 meters for the bird's height, then those extra distances aren't going to affect the answer. Everything near or at the surface of the Earth will always experience about 9.81 newtons per meter as the value of g. And this is why we say, at the surface of the Earth, there is a uniform gravitational field directed down, and we could draw it with evenly spaced field lines. So what if we have a scenario where there's not one planet or mass, but 2 planets or masses? And I'm going to choose a point right here along the center line between the 2 masses, and I want to know what's the gravitational field strength at this point due to the 2 masses together. As always, we imagine putting a small test mass at the point that we're considering. So if I put a little test mass right here, it'll be attracted to this mass, and also attracted to this mass. Now I'm not drawing F, the force, I'm drawing G, the strength of the field. Because G, the strength of the field, is always in the same direction as the force on a test mass. Well, now I just have to add these two vectors together and I get my answer. How do we add vectors? You consider the components. The two x components we see cancel out. The y components are equal to g sine theta, because this y component is opposite the angle theta. The same is true on this side. So the net field is simply equal to negative, because they're both down. When we add the two down vectors up, when we add them together, we get negative 2g sine theta. But what is g? G is this arrow. It's the original field from this mass m. So we can find g using this equation, and we can plug that formula in right here, where m is the mass and r is the distance to the center of each of these objects. We'll see some problems like this.